Conservation of momentum. We've talked about momentum so far. Right? Momentum was P equals mv. And then we talked about the momentum impulse theory, which told us that the change in momentum is equal to the impulse felt, and that was delta P equals F times T. Today's lesson is actually, I think, much easier than yesterday's. Here's why. We're going to not only continue with the idea of with momentum, but now we're going to look at conservation, which we already have. We've looked at conservation with energy. And with energy, conservation said that the energy in the beginning equals the energy at the end. At any point in time, energy is conserved. And the same thing occurs here. At any point in time, momentum is conserved. And what we're going to look at is, with momentum specifically, the interaction of two bodies. So maybe a baseball bat hitting a baseball. Okay, we could find the impulse delivered using the last lesson, but we could also find the momentum using conservation. So in this section, what we're going to really look at is the next. Okay, and it looks like a lot of crazy stuff, but it's not, right? This is exactly what we had for energy. This is the same thing we had for energy, except it said MEI equals MEF, right? This is saying the momentum beforehand equals the momentum after, right? So the momentum at any point in time is conserved. And that momentum is really the sum of all the objects' momentum. So if there's 4 objects beforehand moving, and those 4 objects suddenly combine or they hit together, and then they separate afterward, we could figure out the velocity of each of them afterward if we know enough information. An example of this would be if you've ever played billiards or pool, right? Pool. You hit the cue ball hits another ball. Usually, or not usually, depending on where you hit the cue ball, sometimes you can draw the ball back. Sometimes the cue ball follows the other ball. Sometimes the cue ball hits another ball and it stops, and the other ball moves. And those are examples of conservation of momentum. It's the best example that's possible, because there's very little loss of energy in the interaction of those two cue balls, okay, or those two pool balls. Hockey pucks are another example. Okay, you take a stick, you shoot a hockey puck. Imagine it hits another hockey puck. They're going to collide, and something's going to happen. They're going to move in different directions. Okay, so that's what we're going to talk about here in this lesson. Now, this is only one-dimensional momentum, meaning if an object comes at an angle and the other one goes off at a different angle, we're not really looking at that. That would involve a little bit more cosine, sine, which you can do for sure. But kind of for the sake of time for the year, and I want to get through a lot of topics, we study only one-dimensional momentum, linear momentum. There's also what's called angular momentum. It's something spinning that has momentum. And that was part of the reason. Remember that lab we did? The data came out terrible. Remember that? Where you were in the gym tossing the object up and everybody's data didn't really work too well? After long, after me thinking about this for a while, and speaking with Mr. Donachek, I proposed an idea, and he agrees. He thinks that's what it is. That the object was spinning. When you toss the object, it's not going to move like this, right? That's like a knuckleball. If you've ever tossed a tennis ball to somebody, you throw it. What happens is you throw it. It rolls off your hand, right? So it's going to spin as it's moving. Kick a soccer ball. It's rare that a soccer ball moves through the air like a knuckleball. Alejandro, you know this. Most times when you hit a soccer ball, it's spinning in the air. Even when people throw it in, when you throw it in, you really don't want to spin it. You want to throw it so it's not, but a lot of people it ends up spinning based on the way you release it, based on the way you kick it. When something spins, that is also considered to be energy. And we didn't really consider that in that problem. In the gym that day, we looked at the potential energy at the top, the kinetic at the beginning, the kinetic at the top because it was still moving. But we never considered the fact that it was spinning the whole time. And that might have accounted for the fact that we had that gain in energy when in reality, there shouldn't have been a gain in energy. Okay, there could have been a gain in energy because as you spun it off your hand, as you threw it, it spun, which propelled it forward faster, which increased its velocity at the top, which is what threw us off. That's a good possibility of that. So when Mr. Donachek did this, he did it the other day, and he tried this out after our discussion. He had them throw it so that it didn't spin. So he was having people do something like this, where they were shooting something back and forth like a basketball, but not releasing it like a basketball. When you shoot, you normally roll your fingers off the end of it, right? And you see the ball spins a little bit. He was having them throw it with 2 hands like this. And I noticed in the video their ball was not rotating. And the data he got actually worked. And it worked, I would say, I don't know if it's coincidentally or because of the non-rotation, but it worked to the point where he had just a little bit more energy when it started than at the top, which is what you really should have, because you should lose energy along the way. So in this section, we're not going to look at angular momentum. Nothing's going to be spinning. We're not going to have to worry about 2 objects at angles. It's all going to be linear momentum. Okay, all linear. So one-dimensional linear momentum. So if there's 2 objects that collide or separate from one another, what we could say is that each object has a certain amount of momentum. So in this case, you have, ready? I'll draw it out for you. So imagine you have one object here, traveling this way, another object here, traveling this way. When they collide, what could happen? Give me some scenarios of what could happen. Ellie. They could both go back. They could just stop.
One could stop and one could go.
One could stop and one could go back, right? There's many options here, and our goal in this section is to figure out what is the actual behavior or the moment or the motion of the object after some sort of interaction, whether it be a collision or two objects starting together and separating. But there's going to be some sort of interaction occurring. So what you have here is a simple example when there are two objects, just two objects. If we had three objects, we'd have to have three terms on each side. But before the collision or interaction, we've got the momentum of object 1, the mass of object 1, times the velocity of object 1 initially, plus the momentum of the second object, which is the mass of the second object, times the velocity of the second object initially, meaning before the interaction. Then, after these two objects have collided or expanded or whatever it is, separated, we have momentum afterward. So this is the momentum of the first object afterward. This is the momentum of the second object afterward. There are a lot of subscripts here, if you're noticing. Okay, so please make sure you are neat and meticulous with your work. The majority of mistakes I've seen in the past few years on tests are not understanding. Most people understand this. It's not that difficult. It's the subscripts that throw them off. They make a mistake and write a 2 when it should be a 1, or an I looks like a number 1. So just be careful with your subscripts. If you want to call objects A and B instead of 1 and 2, you could do that. It might be more useful. Okay, so if you want to say MA times VAI plus MB times VBI, instead of calling them 1 and 2, call them A and B. That's absolutely fine because the number 1 does look like a letter I. So that seems to have mistakes along the way, or at least I've picked up on that.
Is this on our formula sheet?
Take a look. You have your formula sheet. Load it. I know that the one I circled is on there for sure. I don't recall if I put this expanded formula. But this formula here is simply saying, ready? The momentum of all the objects before the collision is here. This is the momentum of all the objects after the collision. Where does that come from? It comes from right here. Okay, so you know your momentum formula, P equals mv. That's on your formula sheet. So if you recognize that this top formula just says momentum before equals momentum after, you should just plug in all the momentum before. What if this object on the right here is at rest? What if this object isn't moving? So here's your cue ball. You hit it with a billiard stick, right? A pool stick you hit it with. The cue ball now travels forward to hit another ball that's at rest. What do I do if this is at rest initially? What simplification in this formula can I make if the second object is at rest initially? Ellie?
Just cross out the velocity.
Yep. So right here, that whole thing would be gone. Because if velocity is 0, 0 times the mass is 0. So depending on the scenario, you're not going to have all 4 of these expressions, right? All 4 of these expressions or these terms up here on the board. You might have to drop one of them off. Maybe after the collision, one of the objects stops. Or maybe like, the first object, the cue ball hits this ball, right? It hits it, then the cue ball stops, and the other ball propels forward. Well, then if the cue ball stopped afterward, this would drop off also. Because that's the first object, and it stops after the collision. So depending on the scenario, you're going to be able to eliminate parts of this equation. Okay, simply depending on the given. So a hockey player swings. His stick that has a mass of 1 kilogram at a hockey puck, which has a mass of 125 grams. Notice the different units right away. He swings the stick with a given velocity of 40 meters per second. After the collision, the stick speed is 30 meters per second in the same direction. So we have to figure out what is the actual speed of the hockey puck itself. What is the actual speed of the hockey puck itself? And we're talking about after the collision. So we've got an example here. Let's start by writing down our givens. We know that the mass of the stick, let's call that MA. M1, MA, it doesn't matter. Object A, we'll call the stick. And that's 1 kilogram. Object B, which is the hockey puck, is 125 grams, which is equal to, if I convert it, Katie? Okay. So we have the necessary units up now? Yeah? Yeah. He swings the stick with a velocity of 40 meters per second. then the collision occurs. So 40 meters per second is what?
The initial velocity?
The initial velocity of, which one? Object A or object B?
Object A?
Yeah. Object A was the stick. This is the swing speed of the stick. It's 40 meters per second. So the velocity of object A initially is indeed 40 meters per second. Now, the puck is initially at rest. We're told that at the end of the problem. So what statement can I write from that? If the puck is at rest, I can write?
Well, V, B, I is 0.
There it is. Okay? The velocity of object B initially is 0. It is 0. Now, after the collision or after the stick hits the puck, what's going to happen? I mean, how many of you play either baseball or hockey or some sport where you swing a club or stick? Field hockey? Anyone? No one plays hockey in here at all? You ever play with your friends?
Yeah.
When you swing a stick or you hit something, what happens to that stick or that club or that object? Come on, focus. What happens to it? Yeah, the stick itself is going to feel some deformation and it's going to slow down. Like, I mean, if somebody's pitching a baseball into me and I swing the bat and I hit it, the bat literally feels that force of the ball. So it's going to slow down. So the velocity of the stick after the collision is less than what it started with. And that's logical. It makes sense. It's got to be less. You can't pick up speed after a collision there. So we can write that the velocity of object A after the collision is 30 meters per second. Okay, 30 meters per second. Our goal is to figure out the velocity of the puck. What is its velocity? Right? If the puck is initially at rest, what is its velocity after the collision? So the velocity of the puck after the collision is our question. So that's the information we have here. We can start with the same formula we had up on the last slide. Instead of 1 and 2, though, we'll use A and B. Okay, and we'll see that we can drop off a bunch of stuff. Let's see what we can drop off. So, mass of object A, velocity of object A initially, the mass of object B, the velocity of object B initially. Where am I getting this m times v? Where does that come from again?
Isn't that momentum?
That's the formula for momentum. So again, this, what I've written so far says, the momentum of object A plus the momentum of object B equals. That's how I would literally read that. What can I cross off right away? What can I immediately cross off to simplify this overall governing equation here? What thing drops off that I don't need? Emma? Yeah, right here, this goes to 0. Because VBI, the velocity of the second object, the puck, initially is 0 because the puck was at rest. So there's only momentum in the stick before the collision because the puck is sitting still. Then the stick hits the puck, then they're both moving afterward, so we need both of those terms over here now. If you'd like to, I have no problem with you just not including this entire term because it's 0. You don't have to write out all 4 terms. You've noticed that by now. I do that when we start topics, but eventually, please, you do not need to even write this. Okay, if you recognize right away that there is no momentum in the puck, just write the momentum in the stick equals the momentum in the stick afterward plus the momentum in the puck afterward. You don't need to actually write it. Now, at this point, this is one of the few times I'll say this, and I told you this in the last section. I recommend you plug in numbers. You can solve generically, and if you feel really confident in the math you've had no problems with all year, continue to solve generically. But if you've been struggling a little bit on the math portions, even a little bit, you feel a little bit confused at times, I recommend plugging in numbers because there are so many subscripts that can throw you off here. Okay, that's the only reason I'd say to do that, plug in numbers. Because of that reason, the subscripts can get a little bit overwhelming and easily confused. Yeah?
At this point, could you remove MA from both sides because, like, there's, could you?
Because it's a 1, you could do that. Not because it's the same, because MB is not the same. Look, to remove something from the whole equation, it needs to be in every single term. So MB is over here, so as a result, I cannot cancel all 3. But MA is 1, so technically this is going to be 1 times VAF. So the MA you can actually drop off because it's 1. That's the reason you can drop off MA. Okay? So let's go ahead and plug in our numbers now. Again, MA is 1. I don't need it. I'm going to write it just to be annoying. Times the speed of the stick. That equals 1 times the speed of the stick afterward, plus the puck mass, times what we're looking for, which is the speed of the puck after the collision. Okay, that's what we have in this problem. Stick times its speed equals stick mass times its speed after the collision, plus puck mass times its speed after the collision. What do you notice? When you get an answer here, what kind of an answer you're going to get? You're going to get an answer that is, well, what do you think? Give me something about, I don't want to give it away. What do you think about the answer? Don't give me the actual number. What do you think about the answer you're going to get? Pat? Some characteristic about the answer.
Well, I got a decimal. It's very small.
You got a decimal. Be careful. Did you use 0.125 or 125? And you got a decimal? Check that again.
It's 40 equals 30, and then if you subtract 30 from both sides,
You get 10.
it's 10. And then 10 divided by 0.125.
Not a decimal. That's a huge number. You divide by a decimal, the number goes up,
I
right?
did 0.125 divided by 10.
That's why.
That's what I
That would give you 0.0125.
Yes, that's what I got. 80.
Yeah, now what do you recognize about that? Anybody pick up on this? The answer you're getting is 80. It's not obvious what I'm getting at.
What do you do this 2 times the VAI?
2 times the VA. No, but that's a good thing to notice. I like that you noticed that, but that's not it. That is true. It is double the VAI. Just coincidence there. How much did the speed of the stick go down by? How much? What do you see? Literally. 10, right? So should the puck go up by 10? If they were the same mass, it will. And we're going to see that in the next example. If the stick and the puck were the same exact mass, and the stick speed went down by 10, the puck would go up by 10. It's a transfer of momentum. But the puck mass is 1/8 of the stick. You know your decimals or no? 0.125 is an eighth. Okay, 0.125 is the mass of the puck. That's an eighth of a stick, isn't it? Well, this went up by not 10, by 80. It's the reciprocal of the 1/8. Again, think about it. This is really the number 1/8 here. The mass of the puck is an eighth of the stick. So the speed of the puck is not only going to be the difference of the speed of the stick, which is 10, but it's going to be 8 times that. Again, if my mass is an eighth of your mass and we collide, and you lose 2 meters per second, I'll gain 16 meters per second. 8 times that. Okay? So the smaller object will gain whatever the object's velocity is that it loses, but if they're not the same mass, it will gain that times a factor of the comparative ratio of their masses. So if I'm double your mass, okay, and we collide, and you gain 7 miles per hour, I will lose 3.5 miles per hour. The factor of 2 there. This was a factor of 8 in the mass comparative, or comparison. It really doesn't matter that much in your answer, but I want you guys to see the actual math behind the physics, okay? Why your answer is what it is. A lot of this section, you're going to see a lot of stuff with proportionality because you have nothing squared in the formula. With kinetic energy, this didn't happen because velocity was squared. Remember that? So that was a lot more complicated. You couldn't just do this. But for this, since it's m times v, you're going to see this happen a lot. Where something loses a certain amount, the other thing gains that amount. I hope we're all focusing on physics and not other things. Let's make sure we're looking up and focusing during class. I'm seeing too many things going on that I don't like. Example 2. One soccer ball is kicked down the field and collides with another soccer ball that's initially at rest. Assume the soccer balls are identical. If the ball that's moving before the collision has a velocity of 12 meters per second east before it hits the other ball, and a velocity of 4 meters per second east after it hits the other ball, so it slows down, then what is the velocity of the ball that was initially at rest after the collision? So to demonstrate this, I'm going to simply take a look at 2 pens. Soccer ball 1, soccer ball 2. Soccer ball 2 is at rest. Soccer ball 1 is moving with 12 meters per second east. It collides. It propels this one forward, and then it continues to trail afterward, but slower. So it's moving at 12. It collides. Now this first one is moving on at 4. What do you think this one's moving at?
8.
Probably 8, right? And why do you know it's going to be 8? There's something in this problem that tells you that it actually will be exactly 8. Like this started at 12. It collided. It became 4. Why is this definitely going to be 8?
The difference. Oh, does it because, yeah.
12 minus 4 is the difference, but last time, 40 minus 30 was 10, right? But the answer for the puck wasn't 10, it was 80.
Because they have the same mass.
Yes, very good, Honor. Same exact mass. The masses are identical. So the answer will definitely be 8. Let's prove that true. So we'll start with the formula. I'm not going to write the givens for now, okay? I'm just going to write the formula to start.
Isn't this like the thing where you like take that ball, like there's that like stick and there's like 5 balls and you like take one?
It's called Newton's cradle, absolutely. Newton's cradle is the thing where you drop the one ball and it hits the other and hits the other one. If you drop two of them move. It's all conservation of momentum, the whole thing. Now that's also what's called angular momentum because it's moving at an angle, right? It's not linear. But the idea is the same. It's still conservation of momentum and conservation of energy, both. The reason it stops eventually, Ellie, that device won't go on forever. It will stop eventually. It's because every time there's a collision, you lose a little bit of energy, just a little bit. MB, VBF. So the first object is moving initially, but the second one is not moving. So we can drop that off again. Okay. What else can I do to make this a lot simpler?
Cancel out all the masses.
Why can I cancel out all the masses? Why can I do that, Theo? Because I'm going to divide them anyway. Okay. They're all the same. Thank you. So really, here's what I have. And I'm going to write this even though you don't really have to. This is really what the equation is. I'm simplifying a lot. I'm calling the masses just M now. Why don't I need M1 or M2 or MA and MB? The A and B indicate, yeah, they would indicate different masses because they're all the same though. We don't need them anymore. We did this earlier in the year, and I told you earlier in the year, and we did a problem, and I said, the masses are the same, blah, blah, blah. You could just call them M. You don't need two different masses, M1 and M2. So now, as Anthony said in the last problem, we see that M is in all terms. M cancels out. Does anybody know why they cancel out? We haven't gone over that yet. I've just been telling you to cancel, right, on both sides. Why does M cancel out of all terms?
Because you multiply them on both terms, so they're factors.
Okay, but mathematically, give me more. Yeah, they're factors of each term, so they're in everything, but how would you prove that they actually cancel out?
You just divide the whole thing by M.
Divide every term by M, and the M's all drop off. That's one way. A second way? This is a way that most people don't pick up on, and this is actually very important that you know this, because we're going to see it later on.
Oh, I was going to say multiply them all by 1 over M, but that's kind of the same.
It is the same thing as dividing by M.
Negative M maybe, or?
A negative M. It's not really necessary to do this, but what it's really saying is this. Look, this is really saying this. Right? Isn't that really what it is? Can't I factor M out of the right-hand side? There's an M in both terms. It's GCF, greatest common factor. I could take M out of here and here and put it out in front. And now you have a coefficient of M on both sides. And you've seen this with energy. mgy equals 1/2 mv squared. That was obvious. You cancel the M because there's an M on both sides. God bless you. Now there's a factor of M on both sides. When there's a factor of M on both sides, those simply cancel. Okay, leaving you behind with VAI equals VAF plus VBF, which is the same thing you would get if you cancel M from every term. Okay, but you're really factoring M out and reducing. That's what you're really doing. So as a result, we get this relationship here. The initial velocity of the first soccer ball was 12. The final velocity of the first soccer ball was 4. And our goal is to figure out the velocity of the second soccer ball. So it's apparent and it's obvious and it's clear as daylight now that the answer is definitely 8. We knew that initially because of that conclusion we drew from the previous problem, that whatever the one object loses, the other one gains if they're the same mass. And they are the same mass. So since the first object lost 8 miles an hour, the second object's final velocity is indeed, or meters per second, 8 meters per second. Okay? Again, 12 minus 4 gives you 8. Questions on this one? Making sense so far? This honestly is probably one of the easier topics of the year, and a lot of students do well in this because you're doing the same thing over and over again. You're just changing up the scenario of what objects are occurring or what objects are interacting. Okay, we're going to see in a moment where not objects colliding, but objects are going to separate, or objects are going to lump together. Think about an example of like you're driving a pickup truck and it's snowing. It's really increasing a ton of mass in the truck, which overall affects the overall mass of the entire thing. So it would decrease your velocity. So we're going to see that in an example in a second. A person with a mass of 50 kilograms, I'll demo this even though it's really not necessary. With a mass of 50 kilograms, jumps off of a ledge or a cliff of some sort. and jumps off of this platform with a given velocity, jumping off west, so on this side, okay? Lands on a shopping cart or some sort of a cart with wheels on it, and they begin to move. What is the combined velocity of the two afterwards? So you're literally jumping off of something, landing, and now you're moving together. Does that make sense? So beforehand, you were jumping to an object that's stationary. Afterward, you're moving together as one entity, as one body. Okay? You have an idea of what we're going to do already from that?
Well, I was gonna say, you're gonna have to put in both of your masses in the final because you and that mass are moving as one, thus you need to include both masses together.
Absolutely right. After the collision occurs, there's only one mass, really. It's m1 plus m2. So there's only one final velocity, vf. That's what we're trying to figure out. Very good, Menno. Way to analyze that. Okay, m1 and m2 are separate objects initially, but afterward they're together. So we don't need separate velocities because they're together afterward as one mass. You could simply add the numbers together for the mass and come up with that mass on the right-hand side. This is going to be 70 kilograms because it's really 50 plus 20. Now, on the left-hand side, the person jumps. Okay, the person jumps. So that's the person, MA. And they jump with some velocity, VAI. Is the shopping cart moving initially? Doesn't say anything about it moving, right? So we'll just put a plus 0 or just nothing there, really. The mass of the person is 50 kilograms. The velocity is 5 meters per second west, which means -5. West is negative. Let's keep that up. It doesn't really matter, right? What's the problem? The answer you're going to get is going to be negative because you jump on the object, you're still going to be moving west. So we're going to get a negative answer for VF because our initial was also negative. But this is the problem right here. That's it. So you see how we're taking the formula we started the problem with today? The first formula, PI equals PF, and we're kind of applying it to every scenario. PI, well, initial momentum. There's momentum in the first object, that's right here. There's no momentum in the second object, so 0. After the collision, what's the momentum? It's one object together times its velocity to give you the momentum of the combined person, shopping cart, duo, or whatever you want to call it. Okay, what do you get for VF? What do you get for VF? 250 over 70 with a negative? Why does that answer make sense? There are two reasons. I gave one already. Negative, obviously, because you're moving left, and you're still moving left. Why else does that answer make sense?
It's less than the velocity.
Why?
Why is it?
Yeah.
Because
You're right, you're making a statement, but explain it.
you don't gain speed.
Why? You're on the right track. So the statement was, it's less than what you started with, right? The initial velocity was 5, and now it's 3.6. Forget the negative for a second. Doesn't really matter for this. Want to follow it up?
Is it because you're adding like your mass to the cart?
The cart's mass to you.
Or the, okay.
Yeah.
So the cart's mass to
So if I'm running with a certain velocity, and then suddenly my, younger cousin or something jumps on my back, right? It's going to slow me down. It might give me a nudge first, but eventually it's going to slow me down. I can't run as fast if I have somebody on my back, can I? Think about football players. Football players running on a breakaway, and a guy goes to tackle him and is able to grab onto him. It's going to slow him down. It's not going to speed him up. Because suddenly now he has to pull two masses along with him. So here, this answer has to be less. Because the cart has to also be pushed now. The cart was at rest. Its inertia was 0. Now it's moving, so it has to gain that inertia. Where does it get that inertia from? It gets it from you. Some of your speed decreases so that the cart can move. As a result, you and the cart are moving at a lower rate than what you started with. Okay, it's really important that we understand the answers we get, right? And the actual reasoning behind the answer on the tests. If you get an answer that was like -7, that doesn't make any sense. You can't pick up velocity when you gain mass after a collision. Okay, it cannot have been greater than -5. It cannot have been -6, -7, any of that. Okay?
Is it just a negative because we're moving west?
Yeah.
Why would we?
Yeah, it's only negative because I said west. If it says east, velocity is positive, west is negative. Yep. Okay, same exact problem, Ellie. If I said east, just switch the sign here of -5, which would make your answer also positive because you'd still be moving east then, okay? All right, example 4. Let me guess. Hold on, I have an idea. Alright.
Can I be an ice skater?
You want to be one of the ice skaters? Sure, absolutely. And I need, let's see, Ant, can you come up? I need somebody that's much bigger than the other person. Can you come up to the other one? Thank you.
Do I have to sit?
Yeah, you're gonna sit.
We're gonna push over each other?
I acknowledge it.
Is this synchronized skating?
Hey, please, I wish I was kidding me. Alright, you gotta come closer. Get closer. Sorry, I know it's a little close. Alright. So, I know this is awkward.
This is
Put
like
your hands together. Okay. Now,
This is like the 30.
these are two ice skaters at rest in the middle of the ice, right? They're standing here, they're on a date, going for the ice skating, and they realize they want to push off, and come back together eventually, right? They want to push off. So at the same time, I'm going to count to 3. On 3, just push off. Don't push too hard, but push hard enough, okay? 1, 2, 3. Okay, did he move much?
No.
Did she move?
Yeah.
Why?
His physics.
Because physics.
Mass.
Natalie has less mass than Anna.
Yeah, simple enough, and we did this earlier in the year. Remember when the truck and the car collided, and the question was which exerts more force? The answer was they're the same, but the car has more acceleration as a result. Same thing's happening here. So this is the same concept. Shh, listen, guys. The same concept as inertia earlier in the year, where they push off each other now. So the answer we're going to get here, we need to make sense of. We've got a bigger object and a smaller object, meaning people. So we're going to see our answers and how they make sense. Thanks, guys. So we're going to see how they actually make sense. The answers. Hold on. Right down your givens and try and solve.
What?
Write down your givens and try and solve.
Okay.
Oh my god.
By the way, Dennis for best in physics class, if anybody's watching this video.
Did you ask what?
Dennis is the best in physics class, if anybody's listening at home.
Oh yeah, I know this is true. I didn't think about it. All right. So initially, they are both what? What does it say at the very beginning?
0.
Yeah, they're at rest. So there's no momentum in the system to start. So although we've been writing, like PI equals PF, and we list M1, V1, this left-hand side is going to be 0 for sure. We know that already because they're both at rest. Then Anthony and Natalie pushed off one another, one of them moving with one velocity, the other moving with another velocity. We know that the velocity is going to be different because their masses are different. We also know if one velocity is positive, why? Yeah, Natalie went that way, we'll call that positive. Thus, Anthony had to go that way, we'll call that negative. Okay, so your answer will be negative for sure because the one velocity we got was given as positive. So the mass of person A is 60 kilograms, so MA times VAF, the velocity of them afterward. The mass of the second object times its velocity afterward. Again, why is there a 0 on the left side? Both objects are at rest. The momentum of the system is 0 to start. Okay, this happens a lot. It does. And this is a terrible example to give, but it's a prime example. Think about a bomb. Okay, a bomb is at rest, not a grenade, a bomb. But a bomb sitting still would be at rest, right? With all this internal energy. Afterward, that's before the explosion or collision, it would explode. All the particles shooting from the bomb, all the shrapnel from a grenade, balance in momentum, actually. So if one object goes this way, one will go that way. Part of it goes that way, part of it will go that way. There is a balance of momentum. But before the explosion or collision, whatever in this case, explosion really, the overall momentum would be 0 because it is at rest. Okay? Now, we can plug in what we know. Person A has a mass of 60 kilograms. Person B has a mass of 40 kilograms. The velocity of person B after pushing off is 7 meters per second. So we're trying to figure out the velocity of person A. And this again equals 0. So this is just the momentum balance. Remember in section 6.1, we did an example. We said, what velocity must a bullet have to have in order for it to have the same momentum as a bowling ball? And we found the momentum balance. That's the same thing here. It's the exact same thing. They have to have the exact same momentum, just opposite in signs. Okay, so this answer here is whatever you'll get to give you 280. Right? This is 280, 40 times 7. So this is 280. 60 times what gives you 280 is the question. Now, keeping in mind that it's going to be negative, obviously. Okay? What do we get for VAF? We get for VAF? Katie?
4.7.
4.7 meters per second, and that's going to be negative, right? We're going to have a negative here simply because if we have the negative sign, it counteracts with this positive. Negative plus the positive gives us 0 momentum initially. Okay? Questions on this answer? Again, the velocity was less than 7 because the mass was more than 40. So this was Natalie right here, and this was Anthony right here. Okay? Natalie had less mass, more velocity, it was to the right. Anthony had a little more mass with less velocity, and it was to the left. Okay, it was to the left. Remember the other day when I had that little trap here, and I put those carts on it, and like one of them were colliding? The little spring mechanism that was really not working well at all, that I was like getting annoyed with, that spring, if you compress it and compress another spring and put them together and release them at the same time, would be this exact example of those two things separating from the middle. Okay? Let's look at one more example for today. This is an example here that's a little bit more complicated, but the same concept is applied here. So a pickup truck is carrying a beam in the back of it, in like the what's that called? The flatbed of the pickup truck. It's a steel beam that's very, very massive. The truck is cruising at a velocity of 25 meters per second. Cruising means constant velocity. Cruise control, right? Constant velocity is the word cruising. The beam falls out the back of the truck at a given velocity, and as a result, the truck speeds up. Determine the mass of the truck. Let's go through this because this is not an easy example. I want to demonstrate so you can see it. Here's the truck. Okay? The beam is in the back of the truck. Here's the beam. They're moving together with a given velocity. All of a sudden, the beam starts sliding out the back of the truck. Make believe the tailgate's not lifted up, right? Starts sliding out the back of the truck. Well, what their velocity together as they move is 25. That was given. But as this starts to slide backwards, it means its velocity is going to be less than the truck. It can't keep up with the truck. So as it's about to fall out the back of the truck, the velocity is still moving forward. Like if you jump out the side of a car, you're still moving forward. That's why you would never do that. Like when you're in a car, the velocity of the car is at, you are also at. So if you jump out the side door, you don't stop. You would roll at like 50 miles an hour. That's why people would die from that. You just wouldn't do that. This beam is still moving at 25 until it's about to fall out, and now it's still moving forward, but at 18. Because this truck suddenly lost the mass of the beam, what's going to happen? It's going to speed up. It doesn't have to carry the mass of the beam anymore, so it will increase in speed, and it goes up to 30 meters per second. Okay, that's physically what's happening here. Give me 1 second. I just want to go through the math. Today is an E-day, right? Okay, so yeah, I got to get through this, and I'll take a question. So we've got the pickup truck and the beam together to start. They're together to start. So what could I write if the pickup truck and the beam are together to start?
100 plus 18, 30. Whatever.
What are we trying to find, guys? So we don't know one of the masses, right? But they are together. Very good. Remember in the other problem, we had the masses combined after the collision, like I jumped on the shopping cart and then we were a lumped mass. Now in this problem, you've got the truck right here. You've got the beam, the mass of the beam right here. And since they're together and they're moving together, they're moving at the same velocity. You could write them separately, MAVI plus MBVI, but the VI is the same. So you might as well write them together. Okay. Afterward though, the truck is now still moving with some velocity afterward. That's given, that's 30. The beam is still moving, but it's moving with a different velocity afterward. That velocity is 18. The mass of the beam is 1,000 kilograms. The mass of the truck is unknown. The velocity of them together initially is 25. The mass of the truck is unknown. The mass of the beam is 1,000. Why is this a little bit of a complicated problem? Why is it just a little more complicated than the last one? Honor?
Because you don't know like the individual mass of each.
Yeah. The mass of the object. Look, it's in two different spots. You don't know it. So we have to figure out what to do. To do this, you think about like terms. Let me give you a quick hint. Distribute the 25. Oops. When you distribute 25 to 1,000, it's 25,000. That's one more zero than I need. Equals 30 MA plus 18,000. Now you can just simply solve algebraically. Combine like terms. 25, you can get going. 25 MA comes from the 30 MA, giving you 5 MA. 25,000 minus 18,000 gives you 7,000. Okay, just finish this up tonight. Make sure you do your homework tonight in this section. Okay, you have homework in 6-2. Do that tonight. Office hours are after school. If you want to go over the test specifically, or you're having trouble with this, you want to go over it, please come today after school.